Siendo las 8 p.m., es todo un honor para mí poder acompañarlos y ser el moderador del cuarto ponente del día de hoy, del profesor Fumio Tatsuoka. En cuanto al contenido de la ponencia, tendremos en primer lugar la presentación del equipo GeoUPC. Conoceremos acerca del ponente, el profesor Fumio Tatsuoka. Tendremos la exposición del tema Development of Geosynthetic-Reinforced Soil Structures and the Railway Application. Y bueno, y finalmente terminaremos con la ronda de preguntas. Bueno, voy a presentarme un poco acerca de mi persona. Actualmente soy egresado y estoy trabajando para la empresa minera Cerro Verde como becario en el área de geotecnia en la gerencia de proyectos. Ya, bueno, en cuanto al equipo GeoPC, somos un capítulo estudiantil conformado por alumnos de la carrera de Ingeniería Civil de la Universidad Ciencias Aplicadas, y tenemos como razón de ser nuestra formación como profesionales en el ámbito de la geotecnia. Nosotros conformamos un espacio crítico de investigación donde participamos y creamos actividades para el aprendido de manera teórica a la práctica. Bueno, voy a dar un poco acerca del profesor Fumio. El tema de hoy, como ya se le comentó, es acerca de la geotecnia sísmica, titulado Development of Geosynthetic-Reinforced Soil Structures and the Railways Application. El profesor emérito de la Ingeniería Geotécnica por el Departamento de Ingeniería Civil de la Universidad de Tokio, en Japón. Sus principales contribuciones en la investigación geotécnica incluyen entre la dinámica de suelos, ensayos en tensiones, deformaciones en laboratorio, el comportamiento de suelo-roca, la modelización constitutiva del suelo, los geosintéticos, las estructuras suelo reforzadas, numerosos artículos técnicos y monografías, entre los que se incluyen varios artículos sobre el estado de la técnica y sobre el tema clave. Ha recibido premio a mejor artículo para jóvenes investigadores en 1974, el premio al mejor artículo en el 86, el premio a mejor contribución en el 94, y de la Sociedad Geotécnica Japonesa, el premio IGC en 1994, el premio a mejor artículo en el 95 por la Sociedad Japonesa de Ingenieros Civiles, el premio a mejor artículo de la revista Ground Improvement Journal en el 1997, y bueno, el premio a Jodler en 1996 y 2000 de la CTM y la cátedra de Mercer del 96 al 97. Y por último, fue creador de la revista Soils and Foundation de 1993 a 1999. Doy pase al ingeniero Román para que pueda seguir con la exposición.
Bueno, buenas noches con todos. Mi nombre es Brian Román, como lo mencionó Paolo, soy profesor en la UPC. Es un honor para mí estar aquí presentando a un profesional de grandísima trayectoria, como es el profesor Fumio Tatsuoka. Para, quienes no han tenido la oportunidad de conocer, ha dado muchos aportes a la ingeniería geotécnica. Por ejemplo, el punto de transformación de fase junto al profesor Ishihara. También ha hecho muchas contribuciones en lo que es el comportamiento de esfuerzo de formación de geomateriales, suelos cementados, soft rocks. También ha investigado en lo que vamos a ver hoy día, lo que son estribos integrales, muros de suelo reforzado y su comportamiento sísmico. Hoy nos va a mostrar un resumen de más de 20 años de investigación, todo lo que es estructuras reforzadas con geosintéticos, tanto a nivel de modelo, de prototipo, en mesas vibradoras, en grandes sismos, su comportamiento. Y yo alguna vez tuve la oportunidad de conocerlo en persona, y gracias a las tecnologías de ahora podemos tener también el honor de recibir parte de su conocimiento. So, Tatsuoka-sensei, that was the main. I just want to welcome you
thank you
for this lecture, for your kindness, and please, dos.
May I use my PowerPoint? Yes. Thank you very much for your kind introduction. It is 12 in Tokyo, but it is 11 in Peru.
It's 8 p.m. approximately here, Professor.
Yes. So the topic is developments of the synthetic reinforced soil structures and their radar application. I am Tatsuoka. So this is abstract. The developments of the various types of the synthetic reinforced soil GRS structure with full height rigid facing, including those for high-speed railways, for the last about 40 years are reported. The total wall length of these GR structure has exceeded 200 kilometers. In 1980s, GR retaining wall was developed, for which after the deformation of backfill and subsoil by the construction of reinforced backfill has taken place, the full height rigid facing is constructed, firmly connected to the grid layers. The full height rigid facing is constructed firmly connected to the grid layers by casting in place fresh concrete directly on the grid wrap around wall face. In the early 1990s, I cannot delete this part. In early 1990s, GR's bridge apartment was developed, of which the full height rigid facing supports one end of the simple girder by a fixed bearing. In total, 185 have been constructed. In the early 2000s, GR's internal bridge was developed, for which the both ends of continuous girder are integrated to the top of the full height rigid facing of a pair of GR's retaining walls. 14 have been constructed. A number of conventional type embankments, retaining wall, and a bridge that collapsed by severe earthquakes, floods, tsunami, etc., were restored to GR structures with full height rigid facing. Any of these GR structure has not exhibited problems during and after construction, while very high cost effectiveness has been validated. Oh. Why? Screen does not move, sorry. Huh? Problem. Oh, yes. I would like to express sincere appreciation for great contribution of many colleagues, student researchers, and engineers who joined this very long research project at University of Tokyo, Tokyo University of Science, Railway Technical Research Institute, Japan, Japan Railway Construction, Transport and Technology Agency, a number of railway companies integrated the Technology Institute and many other consulting and construction companies. First is the recent GR structures for high-speed railways in Japan. This is showing the network for high-speed railways. The first one is 1946 here, and this black and white stripes is in service. A red part is under construction. So this part just opened 23 September this year. And the one side for this Hokkaido is shown. Oh, why it does not move? Oh, here. This is shown one side. So R means GR's retaining wall, and A means GR's bridge abutment. and I mean GR's integral bridge, not here. B means the GR's bridge box culvert. And T is the GR's tunnel T here, GR's tunnel entrance exit protection. This is the cross view of the site. This is GR's retaining wall, and this is GR's box culvert, and this is GR tunnel entrance exit protection. This is showing how GR's bridge abutment is constructed. First, with shallow ground improvement when necessary, then construction of the GRS wall, then the so this is the view of at this stage of the GR's bridge abutment, and then we construct the full height rigid facing, then the bridge bearings, then girders. Oh, this is the completed GR's bridge abutment. Here in Kyushu, this just opened. There are a number of GR structures were constructed. Among them, 78 GR bridge abutments were constructed. This is the typical GR's retaining walls. Here, in this route of high-speed railway, 88 bridge abutments were constructed at the tunnel exit, like here and here. GR's bridge abutment were 78. That is 87% of all the bridge abutment. So this is how the GR's bridge abutment is constructed. One is a bench cutting of stable natural slope. Second is the construction of approach fill. That is the grid reinforced, well compacted, lightly cement mixed gravel soil. The third is a compaction of the backfill, at least 95% of load max at the optimal water content by modified Proctor. 4 is the arrangement of the grid layer. 5th is a completed approach fill. 6th is a completed GR bridge abutment after construction of full height rigid facing. Here is a GR tunnel entrance exit protection. GR tunnel entrance exit protection has this structure, and this is the compaction of the backfill, then the arrangement of the grid layer, and this is the construction of GR's walls on both sides of tunnel. And this full height rigid facing, this is structurally separated from RC tunnel lining. This is a typical GR tunnel entrance exit protection. Here you can see. This is showing GR's internal bridge at the place of called Geishu. So first, we excavate subsoil like this. Then the construction of approach fields. Yeah. So this is the grid reinforced, well compacted, lightly cement mixed gravel soil. Third is the construction of full height rigid facing after the deformation of the backfill and subsoil had taken place sufficiently. This is one of the key points of this technology. Then fourth is the arrangement of PC girders like this. This is the cross-section of the girders. This is showing the placement of arrangement of a 30-meter long PC girder. Then the structural integration of both ends of the girder to the full height facing, then construction of slab and others to complete the bridge like this. This is a view taken on August this year. So here's a GR's bridge, integral bridge, and this is continuous RC slab tracks. So why we are using continuous RC slab tracks? The first thing is a relatively high initial construction, but a very large reduction of maintenance cost. This is the maintenance cost for ballasted truck. This is the RC slab maintenance cost for RC slab trucks. At the same time, very small allowable settlement of subsoil, only 10 millimeter per 10 years for required substability, and less than 15 centimeter for required restorability after severe earthquake. This RC slab, continuous RC slab, has not been constructed on the conventional embankments and backfills retained by conventional type retaining walls, as it is difficult to ensure small settlement. On the other hand, the construction of GR structure has been a standard practice, as a small settlement with a high stability can be ensured by good soil compaction, in addition to the use of the synthetic reinforcement with a small vertical spacing, 30 centimeter, firmly connected to the facing. This is a view of one of the 6 similar short span geosynthetic bridges here. So this is showing the history of GR structures. This is the wall length constructed every year. And this is a total wall length. Now, this became more than 200 kilometers. And 2000, the construction of Shinkansen high-speed railway was restarted. And we had a number of big earthquakes here and here, and there are many stories related to these earthquakes. This is showing the locations of completed GR's retaining wall with full height facing, GR's bridge abutment, GR's internal bridge. And so far, the total number of GR structure project sites is 1,412, and the number of GR bridge abutment is 185, and the number of GR internal bridge was 14. So far, no problematic case during and after construction has been reported in all these projects. That is, no problematic case in all these projects. The summary of the first part: a number of the GR structures with full height facing have been constructed in place of conventional type retaining walls, bridge abutments, and bridges. These GR structures have become the standard railway soil structures in Japan. GR structures were constructed also at several overseas sites. This can be attributed to the fact that compared with conventional type soil structures, these GR structures exhibit high performance under long-term ordinary conditions and against severe earthquakes, heavy prolonged rainfalls, strong floods, and tsunami, and the lower cost for construction and long-term maintenance. Second topic is some technical background for this technology. That is, in extensible reinforcement, and the flexible versus stiff facing. This is showing the various types of mechanical stabilized stabilized earth retaining wall. So flexible versus stiff facing here, flexible, not developing high earth pressure, and inextensible versus extensive reinforcement. So the combination of flexible facing and metallic strip is this. The combination of stiff facing and metallic strip is this, B. The combination of flexible facing and extensible reinforcement is C here. And the combination of stiff facing and extensive reinforcement is D, modular block facing, and full height ridge facing, E. Previously, many considered that facing is only to prevent the spilling out of backfill, and for small wall deformation and high wall stability, the earth pressure on the facing should be kept low. So flexible facing, for example, A and C is sufficient. However, we have often observed that when using a flexible facing, for example, A or C, the earth pressure is low, whereas the wall deformation is large, sometimes too large, indicating the paramount importance of using stiff facing. So when the facing is flexible, we have a very low earth pressure on the facing. This results in low tensile forces in reinforcement, in particular at low level. This results in active zone, the low confined pressure, and therefore low strength and stiffness of the backfill. So we have large wall deformation and low stability of the wall. This is a Chiba number embankment constructed in 1982. This has a really flexible facing. So this is a test embankment. With this test embankment, the wrapped around facing is flexible. This exhibited large wall deformation here, already during construction, and additionally by reinforced after construction. Besides, this facing is not durable and vulnerable to ultraviolet light, so not acceptable for important permanent walls. So, on the other hand, we have consistently observed that the stiff facing firmly connected to the facing reinforcement layers, for example, B, D, E here, develop large earth pressure, which results in a small wall deformation and high wall stability. So, when the stiff facing is firmly connected to the reinforcement, then we have a high earth pressure on the facing. This results in high tensile forces in the reinforcement, even after low levels. Then in active zone, high confinement pressure, and therefore we have a high strength and the stiffness of the backfill. So small wall deformation and the high stability of the wall we can obtain. This is a tail armor retaining wall having a discrete panel facing and metallic strip facing. So this is showing a high connection force here and here. This is showing a high earth pressure on the facing and high tensile forces in reinforcement. So this results in a stable wall behavior with small wall deformation. So facing of discrete panel or modular blocks, B or D, can effectively decrease the wall deformation and increase the wall stability. However, for high wall stability, E, full height ridge facing, is more effective and its use is very advantageous in many aspects. This I am going to explain in the following. This is the two test embankments at Railway Technical Research Institute, constructed in 1987 to 1988. So this was constructed to confirm the advantages of full height ridge facing. Here is before construction of full height ridge facing. This is completed full height ridge facing. Number one test embankment is 5 meters, and the grid was used. Number two is a clay backfill. So JR number one test embankment of sand backfill. This is showing the post-construction behavior for 2 years. Segment H here, this is discrete panel facing, show the relatively large deformation. This is the scale of the deformation. Segment D here, F and others of full height ridge facing exhibited very small deformation. Then we perform the loading test to bring the wall to failure. So by using a hydraulic jack here, so vertical loading. This is a cross section of the segment H after having been exposed by excavation. Here's a footing pushed vertically, and we can see a two-wedge failure mode. Then segment H here, discrete panel facing, the zero grid length was 2 meters. The facing backward here, which results in a lowest wall stability. This is the lateral outward displacement at here delta, plotted against the average footing pressure. H shows the smallest strength. Segment F, here, F. This is full height ridge facing, but the length was 1.5 meters. This was more stable than segment H due to the use of full height ridge facing. Here you can see F. Despite the use of the short zero grid, only 1.5 meters. Segment D, full height ridge facing, the length of the grid was now 2 meters. This shows the much more stable. This was much more stable than segment H. This was due to the use of full height ridge facing. However, stability of segment F and D was restrained by yielding of the construction joint CG in the concrete facing. In this test embankment, facing was not steel reinforced. So yielding point here by the cracking in construct joint, the strength did not increase sharply after this point. So all the full height ridge facing of the prototype GRS retaining walls that have been constructed subsequently are all lightly steel reinforced. The summary of the discussion of facing and reinforcement. Here, E, full height ridge facing, firmly connected to the reinforcement layers, can ensure small deformation and high stability of wall, even when relatively short so-called extensive reinforcement is used. So besides, full-height ridge facing exhibits good durability and aesthetic. So these features of full-height ridge facing are discussed in the next section. The next topic is the multiple function of full-height ridge facing. First of all, conventional retaining wall is a cantilever structure. Therefore, we have large forces in the facing, which requiring a massive and strong facing. And we have a large overturning moment and a large lateral thrust force at the facing base. This results in the large stress concentration at the facing base and unstable behavior, particularly by severe seismic loads. So usually we use a pile foundation. This is showing a collapse of a gravity wall. This is one type of the cantilever retaining wall during 1995 Kobe earthquake here. So we can see complete overturning failure despite a seismic design was had been made. So this conventional old seismic design is not sufficient. So we need a more stable walls. So this is GRC retaining wall with full height facing. So GRC retaining wall is not cantilever structure. First, the force equilibrium A here along the potential active failure plane. At each level, the active earth pressure is resisted by the tensile reinforcement layer. This is unlike a cantilever structure. So force equilibrium along the back B along the back of the facing. At each level, the earth pressure on the facing is resisted by the tensile reinforcement layer. This is unlike a cantilever retaining wall. So, full height ridge facing for GRC retaining wall is a continuous beam supported by many reinforcement layers at a small span, 30 centimeter. This is unlike cantilever structures. So, small overturning moment and small lateral thrust load at facing base result. Then we don't need a pile foundation. So and the wall could be stable even against severe seismic loads. This is two types of retaining wall for highway in Yamagata, Japan. This is a cantilever earth retaining wall constructed previously. Then this place, GRC retaining wall with full height facing wall constructed. This is showing cantilever earth retaining wall. This was previously constructed. This is not cost effective because of a large diameter bore for piles and very thick, massive cantilever earth facing. And this is RC retaining wall, a GRC retaining wall with full height ridge facing. This was newly constructed in 1995. This is highly cost effective because no use of piles and full height ridge facing is much thinner than cantilever RC retaining wall. This is showing a GRC retaining wall immediately after completion, 1992. This is GRC retaining wall with full height facing at the Tanata. I took this picture a week after 1995 Kobe earthquake. You can see a full collapse of Japanese wooden house in front of the GRS retaining wall. The wall survived. Yet, noticeable shear deformation, 2.7%, and noticeable lateral displacement at base, by H 2% were observed. This is due likely to the use of short zero grid. Here, this is only 2 meters, 40% of the wall height, H equal to 5 meters. This short zero grid was an exceptional case of the grid arrangement. Then the question is, what is the necessary and sufficient zero grid length for wall stability? So we performed shaking table test simulating retaining walls during 1995 earthquake. This is cantilever gravity-tied retaining wall, the model for gravity-tied retaining wall. This is a model for DR retaining wall. The reinforcement is very short, and these all reinforcers are very short, L by H equal 0.4. This was adopted an exceptional case to avoid an interaction with the existing railway track here on the crest of the embankment. So this was seismically designed by the old court using a low KH 0.2 for allowable safety factor 1.5. This is showing the result of the shaking table test. This is a wall displacement at the top, and this is seismic coefficient K equal to maximum acceleration divided by G. This seismic load was applied stepwise, increasing the alpha max, maximum acceleration. So with a gravity type, we have this displacement. And on the other hand, the GRT wall, this was more stable than the gravity wall, but noticeable shear deformation. So this behavior of two model walls are consistent with the behaviors of the two prototype walls. This is showing the behavior of the other two types of conventional type retaining wall, cantilever wall and leaning type. All these three types of conventional retaining wall, types of retaining wall exhibited similar behavior. On the other hand, R1, this one shows a better performance, and R2, having two long reinforcement layers, exhibited better performance. The performance R2, all the reinforcement is a length of L by H equals 7. The behavior is better. So R2 here is more stable than R1, while similar behavior as R3. So R2 is more cost-effective than R3 because of, 1, less amount of the grid, and 2, less amount of the excavation when constructed on the slope. This is a very important technical point here. So now R2 is recommended as a standard type in the current design code. This is showing zero grid length in the current design. Here, the length of the basic zero grid layer is the largest value among the 35% of the wall height, 1.5 meter, and the length required for residual wall deformation to be lower than the allowable values. This was evaluated for overturning and lateral sliding and by Newmark method based on two-wedge stability analysis and for shear deformation or reinforced zone. So this is showing a two-wedge stability analysis. Stability is examined for all possible locations of point A and B, and all possible angles, theta A, theta B, or failure plane. When the facing is fluid facing, point A is always located at the heel of the footing base, so which largely increases the wall stability. At many places in urban areas, we have a strong need for the reconstruction of the restructuring of a gentle slope to a vertical wall. However, construction of a retaining wall on the slope may require a large slope excavation and use of temporary anchored seat piles. This is an increase in the construction cost and period. With a conventional cantilevered wall, we need a large excavation due to a relatively wide base here. And with the MS retaining wall having a facing of small discrete panel or modular blocks, we also need a large excavation due to use of a relatively long reinforcement. This is required for a sufficient wall stability. I explain next. When the reinforcement, so this is a modular block facing. When the facing, all the reinforcement layers are relatively short, not fully crossing the active failure A here in the unreinforced backfill, then we have a failure plane in reinforcement backfill B here. This is relatively shallow. So the wall stability against lateral sliding and overturning becomes low, particularly when facing is discrete panel or modular blocks like this. Because as the facing is not strong enough, local failure of facing may take place, particularly by a large overturning moment by severe such blows, and other types of failure may take place. So when the facing is discrete panel or modular blocks, to ensure a sufficient stability, relatively long reinforcement, usually L by H more than 0.27, is used to fully cross the active failure plane A and to develop a deep failure plane C like this in the reinforced backfill. Then the large slope excavation becomes necessary, and the use of anchored seat pile may be required. Besides, the use of relatively short metallic strips to reduce the amount of excavation here may result in insufficient throughout resistance. So the use of relatively long metallic strips to prevent the throughout failure results in an increase in the slope excavation and the use of anchored seat piles. This is an increase in the construction cost and period. Compared with two cases having a large slope excavation here and here, now GR's retaining with flat facing having a short base, they're good layers. So this is our design. So a reduction in the wall stability by the use of short basic grid layers is covered by first taking advantage of high throughout strength or planar grid and the use of several long grid layers like this and the use of fluid facing. Then we have a reduced slope excavation and no use of anchored seat piles. This is a typical case of, you can, in Tokyo, you can see excavation here is very small. In particular, the use of several long reinforcement to the plane or reports in unreinforced backfill, and the use of full-height rigid facing, these two enhance monolithic behavior of the enlarged reinforced layer without developing a local failure, which increases the wall stability against overturning and lateral sliding and shear deformation caused by backfill earth pressure, particularly seismic earth pressure, and the stability against external loads like this, which may be applied at or near full height facing. Then this results in the development of GR's bridge abutment and GR's integral bridge. In these cases, girder is supported by full height rigid facing. I'll explain this later. Another important point is that the conventional retaining walls and arctic viaduct, this disadvantage is costly, but they have an advantage that is a limited occupied space and ability to support other structures. In comparison, DRS retaining walls for facing or modular blocks or disc panels, this is less costly, but unlike conventional retaining walls and earth viaduct, we need a buffer zone here to ensure a safe operation of road and railway. So we need a wider occupied space. And then facing cannot effectively support other structures. In comparison, GRS retaining wall with full rigid facing, this is less costly, and like a conventional retaining wall and earth viaduct, railway and road can be located very close to the wall face, so smaller occupied space. And full height rigid facing can support other structures. This is a typical case. You see, this structure is supported by a full height rigid facing. And you see here, railway is located, railway track is located very close to wall face. The summary of the multiple function of full height rigid facing is first, facing is an important and essential structural component that confines the backfill, develops large tensile force in the reinforcement, and can support other structures. So during service, facing should be stiff enough. On the other hand, during the construction of the reinforced backfill, the facing should be deformable enough to accommodate the deformation of the backfill and subsoil. So this contradiction is can be supported by state construction, deformation of facing, deformable facing during construction of the backfill, and we have a settlement, and then finally full height rigid facing. The next topic is the advantage of the construction of full height rigid facing after reinforced backfill. This is the typical state construction of. So this is before the start of construction. This is the stage of the completed backfill, but before the construction of full height rigid facing. This is a completed wall after the construction of full height rigid facing. This is showing the step-by-step construction. So first 1 and 2, start of construction like this. So placing gravel backs at the shoulder here, then the backfilling of and compaction like this, and second layer and third layer. The good compaction of the backfill is achieved by small lift, 15 centimeter, ensured by a small vertical spacing, 30 centimeter, between the grid layers, and no rigid facing here existing during backfill compaction. This is a completion of the wrapped around wall without full height facing, like this. Then after the sufficient completion of the backfill and subsoil has taken place, full height rigid facing is constructed by casting in place fresh concrete here directly on the grid wrapped around wall face. So this is a concrete form, external concrete form, but there is no internal concrete form. The fresh concrete is directly cast in place on this wrapped around wall face. So fresh concrete enters the gravel-filled box through the aperture of the grid. So full height rigid facing and their grid layers are firmly connected to each other. So this is the field and the laboratory test to confirm the high separation strength. This is the field strength. This is a test specimen cut from the 40 centimeter thick scale full height rigid facing, hung under 1G. So there are no separation here. This is a laboratory separation test, the specimen after separation. This is a separation stress plotted against separation displacement. So this value is equivalent to the inertia of 2 meter thick facing by horizontal acceleration 1 meter. This means separation strength is more than sufficient. The property required for the grid is first, sufficient strength and stiffness with low creep deformation. Second, high anchorage strength in concrete and backfill. And third is good adhesiveness with concrete. And fourth is a high long-term resistance against high pH of concrete. So one typical biaxial PVA grid here. These satisfy all these four requirements. So this is the completion of the GRG wall by construction of full height facing. So this is the cross section of the wall. So the advantage of stage construction from 5 to 6 is first, very small residual deformation, differential settlement takes place between the full height rigid facing and backfill. The second is gravel backs here protect the facing the grid connection. So essentially no damage to facing the grid connection during long-term service, even when subjected to severe earthquake. So then the construction of GR's retaining wall using a compressive backfill and or on a compressive subsoil becomes possible. This is a typical case of showing that. We have for this wall, we had a very difficult conditions. Nearly saturated soft backfill was used, and a very thick soft clay deposit, here 30-meter thick, requiring very long piles if we construct a conventional cantilever retaining wall. These problems were overcome by stage construction. First, GRS retaining wall without full height ridge facing and the preloading fill and settlement about 1 meter, then removal of a preload, the final construction of the full height ridge facing. This is a preload fill. Wall height was before preloading 3 meter. This became by preloading to 2 meter. Then construction of full height ridge facing after removal of the preload fill. This is the view 20 years after the construction. So we had several serious problems with a box culvert crossing a road railway embankment on soft soil when constructed by the conventional method. So by conventional method, first piles, the box culvert, then the embankment, then problem starts. Then we have a settlement, then we have a settlement of the backfill. This creates a bump and the load concentration onto the box culvert and negative friction. So this, we have a bump here. A solution by the stage construction of GRS box culvert is like this. The shallow ground improvement, then the zero-grid reinforced embankment, then settlement. Then the construction of GRS culvert. Side walls are connected to GRS layers. Then thin capsule layer, then completion. So, summary of the advantage of stage construction. First, during construction of the up around the grid reinforced backfill, the facing is deformable enough to accommodate the deformation of backfill and subsoil. And during long-term service, even when subjected to severe earthquakes, the stiff and strong rigid facing can keep small the wall deformation, ensuring high wall stability. The next topic is about GRS bridge abutment and GRS internal bridges. So this is showing the developments of GRS retaining wall to GRS bridge abutment, GRS bridge structure. First, this is a conventional simple girder bridge. These have several serious problems. And to solve these problems, the other new structure has been constructed. First is the problem of the conventional simple girder bridges. First, we construct piles, then RC abutment, then backfill is constructed, then problem starts. By earth pressure, RC retaining wall abutment may displace, and settlement and lateral flow of the subsoil by weight of the massive backfill, resulting in a negative friction and bending of the piles, and an increase in the length of and the number of piles. Then we install bearings here, fixed or movable. This is costly for construction and long-term maintenance. And we have a long-term settlement. And the problem of seismic stability of the bridge abutment. This is the collapse of the wing wall and approach field of the bridge abutment during 1995 Kobe earthquake. Then we have a seismic earth pressure and subsoil settlement and lateral flow by seismic load, and low seismic stability at the movable bearing and settlement by seismic load. So what is the solution? First solution is this integral bridge. Integral bridge is constructed by this way: piles and earth facing and continuous gather and structure integration. Finally, backfill. Then some problem. The many were constructed in the United Kingdom, United States, because of the low cost for construction and maintenance by no use of gather bearings and use of continuous gather. However, we have several unsolved old problems. First is the earth pressure and displacement here, and the negative friction and bending of the piles by long-term and seismic ground movement. And gradual settlement and the sudden large settlement by seismic load. This is old problems. In addition, we have new problems. First is we have a seasonal thermal expansion and contraction of the gather. Then we have a cyclic lateral displacement at the top of the facing, because this part is structurally integrated. Then we have a settlement and also increase in earth pressure. This is due to the latchet mechanism. Latchet mechanism. When we have active movement of the facing, we have a formation of active wedge. Then we have a settlement in the backfield. Then we have a passive movement of the facing. Active wedge deforms and displaced as a part of the passive wedge, not recovering the settlement here during active one. So this is the development of the passive wedge. This increases the this results in an increase in the facing earth pressure. Then this is a second active displacement. This results in the deactivation of active wedge. So we have an additional settlement in the backfield. No development of passive wedge at this stage. The second passive displacement, active wedge could form and displace as part of the passive wedge, not recovering the settlement during active 2. Then we have a reactivation of the passive wedge. Then we have an additional increase in the facing earth pressure. This is showing the model test. So we have a small cycle displacement at facing. Here's the sand. In this test, here the earth pressure, lateral displacement is like this. And we have an increase of the lateral earth pressure, K, with the increase in number of cycles. At the same time, we have a settlement here. This is a cycle displacement, and this is a settlement. And this is a active failure in unreinforced backfield by a small cycle lateral displacement of the facing, only D by H equal 0.2%. So another solution is a geotechnical solution, GR's bridge abutment, generation 1 and generation 2. GR's bridge abutment, first generation. First, we construct GR's retaining wall, full height facing, and gather foundation is placed here, not integrated to full height facing. Then movable and fixed gather bearings and girders. So we had no bump right behind the fluoride ridge facing, so low maintenance cost. So this is stable. We have stable approach field and high cost effective. So we constructed several GIS bridge abutment this type. Like this, we performed the field lateral loading test. This will show the very stable behavior. These rather satisfactory performance leading to a construction of many others. However, when the girder becomes long and heavy, first, girder foundation here by large seismic inertial load of the girder foundation where fixed bearing is arranged may become unstable by large seismic inertial load of the girder, and the settlement of the girder foundation due to compression of the underlying vacuum may become unacceptable. So then we move to the development of GIS bridge abutment of second generation. The second generation is constructed in this way. First, the GIS wall, fluoride ridge facing, then girder foundation is placed here. This is made stable by integration to the fluoride ridge facing. Then bearing and simple girder. This is much more stable and much more cost-effective than the conventional type bridge abutment. Besides, this GIS abutment of the second generation is statically determined by the use of bearing. So the internal forces in the girder and facing are not sensitive to their thermal deformation and the displacement of facing if they and displacement facing if they take place. So design of the girder and fluoride ridge facing not sophisticated. For railways in Japan, to minimize the deformation of the reinforced zone, particularly for continuous RC slab tracks, and to ensure high stability against severe seismic loads. This is lightly cement mixed well-graded gravel soil, and this is well compacted and reinforced with the grid layers firmly connected to fluoride ridge facing. Then the grid should have very high long-term resistance against high pH or concrete. Typically, we are using PVA. This is a typical GIS bridge abutment of the second generation. This is the start of construction and construction of the approach field and the construction of fluoride ridge facing, and this is completed one. The summary of the GIS bridge abutment second generation. This is the first one, constructed 2003, and this is the highest one. So first one at Tanaka in 2003, and by 2022, in total, 185 have been constructed, including 41 for Hokkaido High-Speed Railway, 79 for Kyushu High-Speed Railway, and 49 for Hokuriku High-Speed Railway. So bridge placing both ends of simple girder on the bearings at the crest of fluoride ridge facing of a pair of GIS abutment, second generation. This is okay, much better performance and much higher cost effectiveness than the conventional simple girder bridge. So relevant in many cases. However, the following two problems remain. First is the high cost for construction and maintenance of the bearings. and the low seismic stability of the gather at the movable bearing. So we go to the development of, we went to the development of GR's internal bridge. So this is GR's internal bridge. This is a combination of two technologies, GR's bridge abutment and internal bridge. This is constructed in this way. First is shallow ground improvement when necessary, and construction of GR's wall, then full height facing, then this continuous gather and structure integration. So this bridge is to confirm the performance of this type of bridge. We perform static and dynamic model tests to evaluate the performance of the GR's internal bridge. So first is the static cyclic loading test. Here. This is showing the settlement here by the cyclic displacement at the top of the facing, like this. D by H of 0.2%, D by H of 0.6% faster settlement. This is the case, backfill is unreinforced. When the backfill is reinforced, but the reinforcement is not connected to facing, we have a still large settlement like this. When the reinforcement is firmly connected to facing, we have a no settlement, so there are no bump. This is a solution for this problem. We also performed shaking table test. This is the model of the GR's internal bridge. So here the length of the model gather is 61%, and by using mass here, the equivalent length of the gather was made to be 2 meters. So we applied a cyclic dynamic loads here at the base. This is showing a typical test result. dt is a displacement at the top, and dB is displacement at the bottom, plotted against base acceleration. So with conventional gravity type abutment, and here shows a large displacement, and conventional GR's bridge abutment first generation. So small gather foundation is not connected to facing. Then we have a large displacement, and this is an internal bridge without reinforcing the backfill. In this case, we have this large displacement. In comparison, the GR's internal bridge shows a much more stable behavior. GR's internal bridge is most stable, but collapsed by the tensile rupture of the facing reinforcement connection here. So this bridge becomes more stable by increasing the connection strength. So GR's internal bridge is in this one show essentially no settlement here. The other one shows a large settlement like this. So this is showing 4 factors for very high seismic stability of GR's internal bridge. First is the high initial value of the natural frequency, F naught, usually much higher than the predominant frequency of FP of major seismic node. This results in a low response acceleration. Second is a slow decrease in the natural frequency by seismic loading. This is that is high ductility. This results in a slow approach, slowly approaching the resonant state, where F0 equals Fp. Third is large damping ratio due to efficient dissipation of the dynamic energy of the gather and facing to the backfill and subsoil. This results in a low response acceleration. Third is high structure strength. I explained the first and second part. This is showing a decrease in F0 natural frequency with an increase in the base acceleration in model shaking table test. This is a conventional simple gather bridge. So we can see low initial F0, and the F0 decreases very fast and reaches the resonance state. In comparison, GRS internal bridge shows a high initial F0, which decreases slowly, reaches to a resonance state at very high acceleration. We constructed the full-scale model of GRS internal bridge like this, full scale, and completed 2009 at the Railway Technical Research Institute. We performed lateral cyclic loading tests, simulating the seismic and thermal effects. Then we constructed the first GRS internal bridge here. This is completed 2012 for Hokkaido high-speed railway. So you can see slender gather and slender full height ridge facing. This is the result from a structural integration of gather, full height ridge facing, and reinforced backfill. And no bump is developing right behind the facing. So this results in a large cost reduction in construction and maintenance. We constructed 3 GRS internal bridges here for railway here. This is the picture taken 20 days after the 2001 Great East earthquake. So 2 simple girders here had been washed away toward inland by great tsunami from the Pacific Ocean. So this bridge was restored, and this is showing 3 candidates for restoration. This is a 2-span simple girder bridge with 2 pairs of bearings. So this is the same as a collapsed one. The second candidate was single continuous girder with a pair of bearings here. The third candidate is GRS internal bridge without using bearings. Second pair is only to support vertical load. We compared construction cost, seismic stability, and anti-tsunami stability, and need for maintenance. So in all these factors, the GRS internal bridge is the best among the 3 candidates. So this was adopted. This is showing the GRS internal bridge at Kikonai. This is a cross-section, total span length is 40 meters. This is during construction. This is the completed one. This is the view of another place where the bridge, simple girder bridge was totally collapsed by tsunami from the sea. This is the completed one, and the total span was 60 meters. So this is the GRS abutment before the construction of full height ridge facing. This is during construction. Bridge abutment of here without full height ridge facing has been completed, and this is completed one. You can see slender girder and slender full height ridge facing, and no bump here. So this results in a large cost reduction in construction and maintenance. So this is the two GIS integral bridges here. In this case, integral bridges is GIS bridge abutments constructed together like this. This is a GIS bridge abutment and GIS integral bridge. In this case, some ground improvement of the relatively weak surface soil layer. So this is showing that the different patterns of the grid arrangement. For GRT wall, longer the grid used at the higher place. So we use a short basic grid layers to minimize the excavation when constructed on the slope. Several long grid layers are at the upper levels for high wall stability and high stability of the surface soil layers subject to large traffic load. So we may have a different settlement in reinforcement layer and unreinforcement layer, but this difference has no serious effects on the operation of railway and road, because road and railway are running in parallel to the facing. In comparison, the GIS bridge abutment, longer grid layer are used at the bottom. So this is for a low gravity center of the reinforced zone to achieve its high stability against overturning about facing base. And this is to avoid cracking in the brittle cement mixed backfill, which would take place if constructed over relatively deformable unreinforced backfill. Third is train road running in this direction. So for a gradual increase from 0 to in the thickness of unreinforced backfill, like this. So this to achieve a gradual change in the thickness and settlement in the backfill. So smooth running of train and road, particularly important for when we use a continuous RC slab. In actual cases, the shape is slightly different depending on the supporting ground condition. In this case, it's a ground condition very good. So all approach field are cement mixed and reinforced with grit. In this case, it's a rocky gravel, so the bottom part is truncated. In this case, is a approach field for GIS bridge abutment and GIS bridge abutment and GIS integral bridge are constructed together. In any case, the design, all these are designed based on stability analysis. A summary of this part: GIS bridge abutment place one end of the simple girder on a fixed bearing arranged at the crest of flat ridge facing over GIS retaining wall. GIS integral bridge structurally integrates both ends of a continuous girder to the crest of the flat ridge facing of a pair of GIS retaining wall without using bearings. Compared with the conventional simple girder bridges, both this and this are much more cost-effective, exhibiting no bump right behind the facing, while much higher stability against severe seismic loads, strong floods, and tsunami during a long period of service. They are now the standard bridge structures for railways, including high-speed railways, Shinkansen. The last topic is the restoration of soil structures that collapsed by earthquakes, floods, and tsunami to their structures. So this case is here collapsed during 1995 Kobe earthquake, like this. You can see a full collapse of a conventional type retaining wall. This was restored to a GRS retaining wall and or nail walls. Here is a failure of the during 2004 earthquake. You can see the failure of the conventional type retaining wall and slide of the embankment for railway, like this. This was the construct. This is a blue one is cross section before the collapse, and black one is after collapse. The red one is after reconstruction. Here is a GR retaining wall. This is showing construction of flood ridge facing. This is another site. You can see railway embankment collapsed, and this was reconstructed to GR retaining wall. This is the collapse of many railways by Great Tsunami during 2001 Great Japan earthquake. This is a station before the earthquake. You can see a viaduct, RC viaduct here. This was collapsed by tsunami like this. Tsunami came from this direction. Tsunami was 82 meters higher than railway track. This was reconstructed to GRS embankment. This was expected to function as a tsunami barrier. We have many collapse of cantilever type conventional type cantilever retaining walls by scouring at the bottom. So then overturning failure by facing. This quickly followed by the collapse of embankment. On the other hand, GR retaining wall with flood ridge facing is much better performance we can expect. Overturning failure of flood ridge facing by scouring is difficult to take place, so the embankment can survive, keeping the function of the road and railway. This is a failure during Typhoon 2007. This was the collapse of the gravity type seawall for a length of 1.5 kilometers by ocean wave during storm Typhoon. So this is a cross section before the collapse. So this is after restoration to a GRS retaining wall. This is the before the construction of flood ridge facing. Here is the casting in place of concrete for flood ridge facing. This is completely one. This is the Pacific Ocean. This is the collapse of bridge abutment by flood. Here, there was a flood. Then this wing wall or masonry wing wall collapsed by scouring like this. There are a number of similar collapses by floods in Japan. This was restored to GRS retaining walls like this. Importantly, only 10 days was required to reopen the service. This is much smaller than period required to construct conventional cantilever-retaining wall. The construction of full height facing after the opening of service. So this, the last case is here is a collapse of many railways by heavy rainfalls and floods, 2013. This is the collapse of railway embankment, railways here, initiated by the scouring of, at the two of the embankments here. This was reconstructed GR's retaining wall and the great reinforced slope. This is before the construction of full height facing. This is completed GR's structures. This is a full height facing. This is very effective to prevent the failure of the wall by scarring here. So a great number of conventional type embankments, retaining walls, and the bridge collapsed by recent severe earthquakes, heavy rainfalls, strong floods, high ocean storm waves, and tsunami in Japan. Many of them were restored to GR's structures with full height facing because of fast restoration and good constructivity, even at remote places. Second, high stability against natural disasters, even when constructed on steep slopes, and low cost for construction and long-term maintenance. So, concluding remarks. First, a number of GR's retaining walls were full height facing, GR's bridges, abutments, GR's bridges, etc., have been constructed as important permanent structures for a total wall length more than 200 kilometers, many of them for high-speed railways, Shinkansen. This accomplishment is due to their high cost effectiveness by high performance during long-term service and against severe earthquakes, heavy rainfalls, strong floods, etc., and low cost for construction and long-term maintenance. GR's bridge abandonment supports one end of the simple girder on a fixed bearing arranged at the crest of the facing of a GR's retaining wall. This is much more cost-effective and much more stable than conventional type bridge abutment. In total, 185 have been constructed. All are performed satisfactorily with essentially zero bump here. This is now one of the standard bridge abutment structures for railways in Japan. GR's internal bridge consists of a continuous girder of which the both ends are structure integrated to the crest of a full height facing of a pair of GR's retaining wall, not using girder bearings. This is much more cost-effective and much more stable than conventional simple girder bridge. In total, 14 have been constructed. GR's internal bridge is now one of the standard bridge structures for railways in Japan. Many of the conventional type embankments, retaining walls, and bridges that collapsed by recent severe earthquakes, heavy rainfalls, strong floods, high ocean storm waves, tsunami, etc., were restored to GR's structures having full height facing. The following three breakthroughs were necessary to develop these GR structures. First is the use of full height facing for changing from low earth pressure to high earth pressure on the facing, and B, from the facing as a secondary non-structural component to the facing as a primary structure component. Second, a stage construction for a change in construction process from facing before the backfill to facing after the backfill. Third, structure integration of A, fluid ridge facing to reinforce the backfill, and B, GRS, the gather to fluid facing with GRS internal bridge. For a change from a statically determinate but unstable structure to a statically indeterminate but stable one. So this is the last. Thank you very much for your kind attention. So PDF file of my papers you can download until the end of the November 2022.
Thank you so much.
Thank you very much, Tatsuoka Sensei, for such a great presentation. We have some questions now from the audience.
Yes, I had questions.
Yes.
May I use the PowerPoint?
Yes, please. Also,
I had 5 questions. What is the embedment length of GRS bridge abutment? This may be a question about the depth of the backfill. So this depends on the ground conditions. So if the surface soil layer is very soft, this should be removed and should be replaced with gravel layers and so on. Anyway, embedment depth is very shallow. Is my answer is okay?
Yes, very
comprehensive. Second is, okay, what type of soil is most suitable to use as a backfill to reduce the bump in the GRS department? Yes, well-graded gravelly soil. Well-graded gravelly soil is the best. But sandy soil is okay if they are well compacted. Clay soil is not good because compaction is very difficult. Maybe this is my answer. And third, what is software did you use for the geotechnical and structure design of the GR structures? We have a software. It's an engineer using a software to make a design of the wall and GR structures. So this is written in explanation is written in Japanese, but now they are translating this explanation into English because several projects are now outside Japan, Vietnam, Philippines, Indonesia, maybe India. And if somebody like to get, I can give you the manual of design and construction in English. In English, this is rather thick. So I'll send this later to the coordinator. Software is I cannot distribute because
it was. Did you say it was designed by? It was developed by GR company.
The consultant and also Japanese Railway Technical Research Institute.
Yeah, I guess. I got it.
4. What is the strength of the concrete used to fluid facing? It's ordinary or nothing special. Ordinary concrete is okay. We don't need a special. We do not need a special concrete. 5th, in what cases do GRS bridge abutment use piles? So far, 185 GRS bridge abutment were constructed, but no case using piles. if we use a pile, we lose some good advantage of this GeoUPC abutment.
Have one last question.
Yes.
Would it be possible to improve the performance if the geogrids were biaxial or triaxial geogrids?
Excuse me, what?
The geogrids, if they were biaxial or triaxial geogrids instead of...
we are using a grid is okay. 2 ways is okay. We need a triaxial because for one main member is in the direction perpendicular to our face, and the other is transversal one to make the behavior monolithic. So grid is okay. 2 ways are more than sufficient.
Okay. With that, I think we can finish today's presentation. Dosu arigatou gozaimasu, Tatsuoka sensei.
Okay. So no more questions. So
¿Más preguntas, Paolo?
Okay.
Creo que ya con su...
So we can finish my lecture.
Yes, I think we can finish now.
I enjoyed my talk. A bit too long, but okay. I hope you have somehow enjoyed my lecture. Yes, I hope.
Yes,
okay.
We did, Professor.
Okay, bye-bye.
Bye, Professor. Thank you so much for excellent presentation.